So we are going to finish the risk management part this week, this lecture. And I will post a homework set and a project today or tomorrow for you to complete during the reading week, right? During the rest of this week and a reading week. It's a lot of time. And midterm will cover up to today's material, starting from the week after midterm, reading week. Then we will actually do the second part of portfolio management. Mainly we focus on the mean variance approach. And so let's begin. Let's review, because remember that the value at risk var is blind to the tail. So you can recall what is blind to the tail from the previous lecture. Because of that issue, we introduced the expect shortfall. So let alpha less than 1, larger than 0. For a loss operation, the expect shortfall at a level alpha of a loss operation L is defined as the average of the value at risk. So value at risk. If you choose a single value value at risk is not very good. So keeping in mind what is the value at risk, pretty much it is just for example, if you have the standard normal distribution, this is a CDF. Value at risk is just if you give me a label U, then the corresponding X is just pretty much it is just if you have an inverse, if a capital F has the inverse, then it's just an inverse function. If it does not have the inverse, then we introduce it as define it as a generalized inverse. Okay. So pretty much, at this value, L is less than or equal to this value with probability alpha. Pretty much, it's not exact. It's not exactly true, because if the inverse exists, that is the case. If the inverse does not exist, it's not accurate. So basically, it's just a quantile function. We talk about the percentile, right? Percentile, right? For example, if U is 90%, right, or 0.9, okay, U is 80%, or maybe 95%, right? 0.95. So the value of risk at alpha U equals 0.95, which is 95% percentile. 95%, more or less, 95% L is less than or equal to this value. 5% of a chance L is larger than or equal to this value. So now basically it's the tail values of your loss position, right? So value risk is tail value. Now we integrated this over this interval on an interval 1 alpha to 1, right? We take an integral of this one. How long is the interval? Well, the length is 1 minus alpha. So if you divide 1 minus alpha. So what you end up is that this is just the average of a tail values of L, right? But you are cutting off at the alpha level. Okay, so it's a tail value. Let's review our example for a discrete random variable. Then we will talk about more things about it. So example, let's do some hands-on example, then you will have more feelings about it. So given L, satisfy this one, L equals 1 with probability 0.3, L equals -1 equals probability 1. Probability of L, this is a discrete random variable, you can see. It takes only 4 values. Right? It takes 4 values with different probabilities, right? So in order to calculate the expected form, so find expected form point, let me do 0.55 of L. Okay, I want to calculate expected form of L at 0.55. So by definition, you have to calculate the value risk first, right? You know the value risk, then you compute the integral, right? So let's do method 1. Assuming I will introduce a method 2 for discrete random variable. Method 1. Okay, for discrete random variable, I'm going to introduce 2 methods to compute a value risk. This is method 1 using the definition. For random variables with the probability density function, I will also introduce 2 ways to compute them. So you need to know both ways. Method 1. So we need to find the value risk, right? So recall F alpha is the left continuous non-decreasing rearrangement of L. If the quantile function is just rearranging the values of L on the interval 0, 1. Now observe, note, L takes the values. Do it from the smallest one to the largest one. It takes 4 values. Smallest one is -2, then -1, then 1, then 2, from smallest to largest, and with probability. With probabilities, for -2, the probability is 0.5, -1, the probability is 0.1. Then for the value 1, the probability is 0.3, and for the value 2, the probability is 0.1 again, respectively. From here, we immediately get the graph of this one. By the way, this is just the value risk. Value risk is defined as F left arrow alpha of alpha. So how do you get a graph? First, you mark the from 0, 1. Okay, from 0, 1, 0, 1. Alpha this is alpha, the axis for alpha. Right? F left arrow is a function of alpha, right? Alpha is probability between 0 and 1. So now look at the smallest value. Smallest value is -2 with probability 0.5. So first of all, you make a integral, start with the smallest value. Look at the probability 0.5. So this is your interval 0.5. And the value is -2. So the value is -2. So on this interval, F left alpha, F left arrow takes -2 value. The next value is -1, and the probability is 0.1. So you choose an interval of length 0.1. So this is 0.5. This is 0.5. The next interval is 0.1. 0.1. 0.1. And the value it takes is -2, is -1, sorry, -1. The next value is 1. And the interval is 0.3. So you need to choose the interval of 0.3. 0.3. The interval is 0.3. And the value of f left arrow is 1. The next one is the next value is what is 2, right? With probably 0.1. Of course, the remaining interval has length 0.1, right? And the value of the function of the random of f left arrow is 2. So 2, 1. This is -1. Okay. Remember, so you can see this is we only need to add on the left continuity, right? So continuous from a left, so this point at a by the way, this point is 0.5, right? This point is 0.6. This point is 0.9. Okay, the last endpoint is 1 for sure. So you can see from here that yeah, we only need to add on the left continuity. Okay, f left arrow must be left continuous, continuous from a left. Continuous, so at this piece, continuous from a left, at this piece, continuous from a left. Done. This is a graph of f left arrow. F left arrow. Okay, if it really distributes its value like x, like your original random variable L. Okay, L takes the 4 value, -2, -1, 1, and 2. So your valid risk has also 4 values, -2, -1, 1, 2. Right? L takes the value -2 with 0.5. So over the interval, how long is the interval? With length 0.5, you have a value -2, right? So it's a rearrangement. So now we need to compute. Now we need to compute this expression for ES 0.55 of L. So my alpha is 0.55. So I need to integrate 1 minus 0.55. Integrate from 0.55 to L, right? To 1. So 0.5, where is 0.55? It's pretty much from here. Right? This is between 0.5 and 0.6 is here. Integral means means area, right? So this part, and then this part, and then finally the last part. Integral means area. You can do integrals. You can do or find of. Let's do integrals. So it will be 1 minus 0.55. You have to integrate. There are 3 pieces, right? Okay, 3 pieces. Integrate from 0.55 to 0.6. And the value of the function is -1 du. Then from 0.6 to 0.9, right? And on the second piece, this piece, right? The second piece, the value of a function is 1, right? Du. And then integrate from 0.9 to 1. And the value of f left arrow is 2, so du. This is what you have. Okay. If you compute this integrals, or if you just do the integral of the rectangles, because they are rectangles, it's easy, right? If you do the integral in the rectangles, it's what is the length of of the first rectangle. 0.6 minus 0.55 times the height is -1. And the second one is from 0.6 to 0.9, right? So 0.9 minus 0.6, this is the length of the bottom. What is the height of a second blue rectangle? 1. For the last piece of rectangle, right? So what is the width? It's a 1 minus 0.9, right? Times the height 2, right? So if you do, now you can use a calculator to do this, okay? This is how you do it. This is how you calculate the expression form. Now we need to look at this more carefully, what it really does. I suppose no question about the computation, right? Because we talked about them in the previous lecture. I just resume the example. This is 0.5, 0.6. This is 0.9, okay? And this is 1 coordinates. So if we really think about what we have done is that we are looking at the largest tails. Right? We are looking at the largest tails. First of all, the largest tail we're looking at is 2, right? Started from the largest tail. Because F left arrow is pretty much the percentiles, right? Okay, percentile. Let's see, percentile 95 percentiles, and it means the random variable is pretty much 95% below this value. L is the probability of L below this value, percentile is 95%. The L is above this percentile is 5% chance, right? So they're pretty much tails. For discrete random variables, you are what do you do is that you are choosing a probability of 1 minus alpha. We are looking at a 0.55. So 0.55 is here. This point is 0.55. It's between 0.5 and 0.6. And we are looking at the average of the average values, right? Average value. What is 2? 2 is actually, remember this has the same value as L, right? Probability of L equal to 2 with probability 0.01, the largest value of L. The second largest value of L is 1, the probability is 0.3. The third largest value of L is -1. Then the smallest value is -2, right? The 0.5, that's 0.1, right? These are the values of L. When we do the averages of the quantile of F left arrow, F left arrow just rearranging the values of L, right? So when we do this, what we actually do is very easy to see now. You take the largest value of L. The largest value of L is 2. Consider the largest value of L. It involves largest value of L. Value of L, which is 2, right? The probability of this, probability of L is of 2, taking 2 is 0.01, right? Okay. So the second largest value, second largest value of L is 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 1, right? And the probability is 0.3. In total now is 0.4. In total now is 0.4, right? In total now is 0.4. The third largest value of L is what? Of L is -1. The probability is, what is the probability? 0.1, right? Probability is 0.1. If you take the three pieces now, what is the total probability? 0.1 plus 0.3 is 0.4, right? Plus this, you will have 0.5. So that's too much because we are averaging from 0.55 to 1, right? So that we are averaging over the total probability we want to average about is what is 1 minus the interval is 1 minus too much. Is 1 minus 0.55. So it's the total length we're looking at is actually 0.45. So what do I do? Let's take what we want. If we take a 0.55, then the total length. Now if you add them together, 0.1 plus 0.3 plus 0.05, the total probably is 0.45, exactly what we want. So basically, when we do the average, we are looking at what? We are looking at three pieces, right? See, the last piece. This corresponds to the largest value of L. Okay. Then we look at the second largest piece. This corresponds to the second largest value of L, 1. The probability is 0.1. Then we look at the third largest value. Because now the total probability is 0.1 plus 0.3, right? It's not enough. We're looking at the interval we'll look at. What is the interval we'll look at? The 0.55, you see 0.55 to 1, right? To 1, right? So the total length we're looking at is 1 minus 0.55, 0.45. So now we consider two largest values of L. That'll give you probably 0.4. Not enough. So we need one more piece. And the one more piece we're looking at is this one. The third largest value, -1. But we only take it to a little bit of probability, not the entire piece. We only take a probability 0.05 because this now we are arriving at total probability 0.45. So when you compute the expression of L at a probability at alpha equals 0.55, you are just looking at the largest values of L, the largest of them, okay? Largest of them. And you want to take an average of them, okay? You're not just looking at one tail, look at average. So how do I do this one? If I sum up, right, how do I compute expression of this one? It is average of the largest equals average of the largest value of L, which is 2 with this much probability. And the second largest value of L, which is 1 with this much probability. And the third largest value of L, which is -1. And it equals 0.05. So if we understand the expression of this way, then it's much easier to calculate, because you see the largest value was probability 2, also 2. Okay, what probability you use is 0.1. The second largest value of L is 1. What probability you use 0.3. The third largest value of L you use is -1, and the probability is 0.05. You see, you are doing average, so you should do the total probability you use is 0.45, right? If you check this one with the previous value, you should get the same answer, right? We're just rephrasing it. Does this make sense to you? Okay, it should make sense. Now we are going to rephrase what we do in another way. Instead of now, I described this idea I described this way, right? For discrete random variable at least, right? You just take the largest value of L the largest value of L, consider its probability. Then the second largest value of L, consider its probability. Then the third largest value of L. You have to be careful. The total probability you need to accumulate is 1 minus alpha. Okay, the total probability you are going to do is 1 minus alpha. My alpha is 0.55, so 1 minus alpha is 0.45, right? So I don't need to consider the fourth value because so far I have 0.1 plus 0.3 plus 0.05. I have 0.45 as I want. So it involves three values. Yeah, another way you can summarize this as this one. Instead of using the graph of f left arrow, I can also get back to how does recall L is a random variable on a sample space omega, right? So pretty much omega, let's say omega looks like this. Now I know if this is my omega, it means that on a part of omega, L takes value 2. Let's say on this part, L equals value 2, right? Omega is the entire sample space. L is pretty much a function defined on omega, right? Defined on omega. So on a part of L with probability 1, right? Your L equal 2. On another part of omega, L equals 1 on this part of omega, and the probability of this part is 0.3. On another part of omega, sorry, L take on this part, L takes value -1, right? The probability is 0.1, right? Agree. So now on a remaining part, L takes value -2, and the probability of this part is 0.5. Pretty much this is how you define L, right? Do you agree with me? Okay. So now what we have is this. Now if I look at this one, now I consider expression of what is expression of this? Remember, it's the average of largest values of L of a set of probability 0.45, 1 minus alpha, remember. So if you look at compare with before, you are looking at the average of a largest value of L. From the largest one is 2, then the second largest is 1, until you accumulate a probability of 0.45, right? So average of largest values of L over a set of probability 0.45. Agree? So using this one, actually, this is very easy to compute, right? Using this idea and a graph of the situation of your of your omega. How do you define this one, right? Combine this graph. Combine this graph together with this description, right? Okay. Average of the largest values of L over a theta is probably 0.45. The largest value of 0.2 is fine. 0.2, sorry, the largest value is 2, right? And the probability is 0.1, not enough. The second value is 0.1 with probability 0.3. So in total, you have probability 0.1 plus 0.3, total 0.4. Not enough. We need a 0.45. What do you do? What do you do is that, okay, so far you have accumulated 0.4. So the next largest value is -1, right? The total probability 0.1 is too much for me, so I take a part of it. I take a part of it. I don't take the entire piece. How much do I take? 0.05. Okay. If I do this one, life is easier. Life is easier. Let me show you. Oh, I just need to take an average of L, largest values of L with probability 0.45. So like as above graph, right? Oh, the largest value 0.2 with probability sorry. The largest value 1 times the probability 0.4 or 0.1 plus the second largest value is 1 times probability 0.3. The third largest value is -1 times the probability. How much do I need? How much probability do I need? Probability 0.05, right? So times 0.05. This is the entire thing. You have to do the average, right? The average is divided by 0.45. Immediately get that. What is the advantage of this method? This is my method 2. This is my method 2. What is the advantage of this method 2? Advantage of this method. You don't need to graph. You don't need to graph the F left arrow, right? You don't need to graph this one. As long as the discrete random variable, you just look at the values of L. Okay, starting from the largest value, we're always averaging the right tail, right? We are right tail of L, means largest value. Starting from the largest until you go down to the probability you want, accumulate enough probabilities. How much probabilities? In my case, it's 0.545. Why is that? It's 1 minus alpha. It's 1 minus alpha. Let's do one more example. The example. I have a random variable probability of L equals 5 with probability 0.3. Probability of L equals -5 with probability 2. Probability of L equals 1 equals 0.4. Probability of L equals -2. This is my random variable. First of all, I ask you to find expect shortfall of 0.95 of L. Then find expect shortfall of 0.6. Right? 0.6. Then expect shortfall of 0.3. Let's see. Let's see how I do it. So first of all, solution. My solution is that first of all, I want to rearrange them. Rearrange these according from the largest to smallest, because I'm going to accumulate the largest values, right? The largest value is L, P of L equals 5. And the probability is 0.3. Then the second largest value is L equals 1. The probability is 0.4. Then probability of L equals, the next one is -2. And the probability is 0.1. Then the smallest one is L equals -5 equals 0.2, right? Okay. So I'm rearranging the equations, the probability mass function basically. From a largest value 5, the next one is 1, the next one is -2, the next one is -5. Okay. So now life is easier. I don't need to draw any graph. So compute of this one. Alpha is 0.595. So what is the tail probability you are looking at? 1 minus alpha. 1 minus alpha. So what is it? So the bottom is always 1 minus alpha, right? The bottom is 0.05. You need to accumulate. You need to consider the largest values over the probability. Largest values. Consider largest values with probability 1 minus 0.95, which is 0.005. Oh, there is nothing to worry about because the largest value is 5, and the total probability is for this value is 0.3. It's more than enough, right? It's more than enough. Basically, you just take a L on omega, right? There is a big portion of L equals 5 with 0.3. And you only need a probability 0.05, so you take a small part of it, right? Okay, so nevertheless, the first value is more than you need. So you just take a 3 times the probability 0.5. Okay. Average is the value times the probability, right? How about this one? Expected of 0.6. 0.6, right? So you need to consider the average of 1 minus 0.6, the average of probability. The probability, you need to consider the largest values with probability. How much? 1 minus 0.6 equal 0.4. Okay. You need to consider largest tail value with probability 0.4. But if you look at the largest value of 5 is 0.3, only 0.3, not enough. I need a little bit more from here, right? So what is that? 5 times 0.3 plus the next value is 1 times 0.1. Now I have total probability is 0.4. Probability 0.4. Enough. Okay. Let's finish this example, then we can have a break, right? Oh, no, not a break yet. It's too early. Let's finish this one. So then let's do the next one. Expression of this one. Oh, so this is the largest value with probability 1 minus 0.3 equals 0.7. Okay, 0.7. 0.7. So 1 minus 0.3. 0.7. I have, if I start with the largest value 0.3, the next value is 0.3. So you consider two values exactly. So it's 5 times 0.3 plus 1 times 0.4. Now you have exactly 0.7 probability, right? Let's do one more. Special of 0.25, let's see, of L. Oh, I made a mistake. This is 1 minus 0.3. 1 minus 0.3. Right. So this is 1 minus 0.25. So you have you need to consider the largest values with probability 0.75. So you consider 0.3 plus 0.4. You need a little bit from here, a little bit from here, right? So this is 5 times 0.3 plus 1 times 0.4. Now the total probability is 0.7 already, right? So you need a plus minus 2 times 0.005. Plus this one, you have 0.05, 0.75, right? That's it. You don't need to do graph. You don't need to do graph, make any graphs. You don't, okay. So let's compare a little bit. If you use definition, if you use definition to compute exponential form, right? You have to graph, make a graph of the f left arrow, which is easy to graph, by the way, because it's just it's what? It's just a rearrangement, left continuous rearrangement of left continuous non-decreasing rearrangement of L. So you can easily draw a graph of f left arrow. Then you do the average or integrals as you wish. So this is called definition, method one using definition. Right? Method one using definition. Using definition. Okay, right? Because you're using integrals, right? Definition. Right? The second method is easier because you don't need to draw any graphs. It just does, using this part, using this assertion. What is my assertion? Maybe I state it as a proposition or theorem. Let me state it as a theory. Theorem. The spectral form of alpha of L equals average of largest values of L with probability 1 minus alpha. Okay. First of all, you consider the largest values. Start from the largest values of L. But how many values do you need to accumulate up to the probability 1 minus alpha? Okay. So this is second method. And the second method is backed up by this one, by second method. Okay, this is second method. It's based on this theory. And there is a question. Shouldn't it be 5 times? No, 5 is the largest value, right? You start from a largest value. Oh yeah. You are talking about. I understand now. You're talking about this part, right? This is a typo. This is a typo. Typo. This should be 5. The largest value 5. Thank you. So now, yeah, thank you. So now let's I have talked about 2 methods of computing exponential form. One, mainly I use the discrete random variables. For discrete random variable, at least you have 2 methods. One is using one is using what? One is using the definition, right, for discrete random. The second one is using this theorem. Exponential form equals the large average of the largest values with probability 1 minus alpha. So I'm going to make another observation which will be crucial. So I can consider expectations. So here you just consider the values, the averages, the averages of largest value. Average means averaged by their probabilities. Okay, not just adding them together. For example, of value 5. Probability is 0.3. You have to value times probability, right? Value times it's like expectation. Agree? It's like expectation. What is expectation? Value times probability. Add them together, right? So here, if you think about it, what is it? We can connect it with this one. So I can consider expectation of X on the sets with probability 1. So omega, you can define omega, so let's say A with you can find on omega. What can you do? You can find a lot of sets with probability of 1 minus alpha, right? If I cut it this way, I can find another set with B probability 1 minus alpha. Maybe I do this way, right? Another set probability C with 1 minus alpha, right? I want to consider expectation of X on a set alpha. We have seen this function. If omega inside A, it takes the value 1. If omega is outside A, then it takes a value 0. This is called indicator function, just an indicator of the set A. It takes only two values, either 1 or 0. Either 1 or 0. Either 1 or 0. So what is X times this one? X times this one. So at omega. If omega is inside A, then indicator of A is 1 times X, is just X of omega, right? If omega is not inside A, then indicator of A of omega is 0. So X times 0 is just 0, right? Okay. So if we consider this one, it's just expectation on, what is this? Oh, on A, I take an expectation of X. Of A, I put it to 0. So you're just the expectation of, this is expectation of X. Expectation of X on the set A. Right? On A, it's just X. Of A, it's 0. Right? Of A is outside A is 0. X, the new random variable X times indicator of A just 0, right? So this is expectation of X on A, right? So what is this? Expectation of X is divided by probability of A. What is that? This is just the average of X on the set A. Right? Can you understand this? If you have taken if you recall from MTH 304, previous like multiply 3 with 3. This 5 by, where did I have 5 times 0.55? That is a mistake. -2 because look at here, the last case, right? This is 0.75. This is 0.75. I need to accumulate to probability 0.75. So I started the largest value, 0.3. Oh, not enough. 0.4, that gave you 0.7 total, right? Not enough. You need a 0.75. So you need to take some, right? So this is pretty much 0.3 plus 0.4 plus 0.005. This gave you 0.75, right? Okay, so that means for an entire L equals 5, take it. For an entire L equals 1, the value 1, take it. Now for a largest value -2, you cannot take a 4 of this. If you take a 4 of it, the probability will be 0.3 plus 0.4 plus 0.1. That will be 0.8. That's too large for us. So I only take a 0.05 of it. Okay. So for the largest value 5, I use it 4 for probability 0.3. For the second largest value 1, I use it for a 4 probability 0.4. For third largest value -2, I use it for partial probability, only probability 0.05. Now add together, you have probability 75, right? Okay. Let's give you probability 0.3. Let's give you probability 0.4. Together you have 0.7. But what I want is 0.75. So you need the next value you only use for the remaining probability 0.05. In total now you have probability 0.75. Yeah. Okay, that's why. You can also see it from the previous example where I draw a graph illustrating it using L. Okay, you can review afterwards. Always keep in mind, you have to accumulate to the values with probability 1 minus alpha. You have to accumulate it with probability 1 minus alpha. Okay, okay. From the largest values, you have to make sure you have probability 1 minus alpha. So here is 0.3, the largest value. Second largest value is 0.4. In total, you have 0.7. Not enough. You need a 1 minus alpha. For this question, alpha is 0.25. So 1 minus alpha is 0.75. Okay, you need a probability 0.75. So 0.3, 0.4, not enough. You need another one additional piece, 0.05. And for the 0.05, the value is -2, the third largest value. Does it make sense to you? It's okay. So let's continue. What I'm going to talk about is this one. So X, first of all, we need to understand what is indicator function. Indicate, you are indicating whether omega is inside A, right? If omega inside A, it equals 1. So now X times this one, right? Inside A, it equals, if omega inside A, then the random variable takes the value just X omega times 1. Outside A, X omega times 0, which is 0, right? So on A, it is still X. Outside A is 0 now. Now you take expectation of this guy. What is it? It's just expectation of X on the theta A, right? On A, it is still X. Outside A is 0 now. If you divide it by the probability of A, what is it? You are taking expectation of X on A. You divide it by the probability of A, it's like the average of X on a theta A, right? If you recall from the MTG 404 or 304, this is a conditional expectation on A. Or conditional expectation on A. Or expectation of X on conditional expectation. You can check your notes from MTG 304. This is conditional expectation on A. Right? So what is conditional expectation on A? Means restricted on A, what do you expect? Expectation means average, right? So on A, what is the average of X? See, right here. Conditional expectation of A. So conditional on A, what is the average of your X? Okay, and how you define it? Yes, the overall expectation of X on A divided by probability of A, right? So now the thing is that I can find many seats with probability 1 minus alpha. I claim that theorem. Expect shortfall alpha of L is just, we consider a lot of seats with probability 1 minus alpha. I consider the maximum of this. So what does this mean? For any seat with probability 1 minus alpha, for any seat, you find the probability of 1 minus alpha. For any seat with probability 1 minus alpha. You compute the conditional expectation of X. You consider the conditional expectation of X on A. I claim expectation shortfall is the largest one of them. But you can find a seat A1 with probability 1 minus alpha due to conditional expectation. You can find another seat A2 with probability 1 minus alpha due to conditional expectation. Okay, so you find many values of the conditional expectations. Expectation shortfall is the largest value. That's my claim. Why is that? Let's come back to our example before. Look at this one. When you do expect shortfall, right? Look at this example. When you do expect shortfall with alpha 0.55 of L. So this is the average of the largest values of L over a seat of probability 0.45. Do you see that? I find the largest seat for you, the green parts. Right. The green part is what is the green part? What is the probability of a green part? L equals 1, the probability is 0.3. L equals 2, the probability is 0.1. L equals minus 1, the probability I choose is 0.05. So in total, the green part has probability 0.45. Probability, let me write it down here. Probability of green part is 0.45. Do you agree with me? The green part of omega. This is the seat A I'm using. This is the green part is the seat A I'm using. This is a seat. This is a seat A with probability 45. With probability 45. Okay, this is a seat with probability 0.45. Can you say that when you compute expect shortfall, it's right here. You are just doing the average or the conditional expectation of X on the theta A. What is the conditional expectation on the theta A? Just the expectation of X on the theta A, right? On the theta A, just the value L itself. Outside A is 0, right? So it's what is the expectation on the theta A? It has how many values? Value 1 of 2, 1, -1, right? 2 with probability 0.1, 1 with probability 0.3, and then the next value is -1. The probability you are using is 0.05. The total probability of A is 0.45, right? So in the blue box, right? In a blue circle, right? That is a computation of expectation of what is it? Average of the largest values of L of a seat of probability 0.45. The seat is just the A I mark for you. Okay, this is the seat I mark for you. If you do another seat, you will find that your expectation would be smaller. Let me show you. On this particular seat, you can compute the expectation for it. Let's resume the previous example. If you use another seat A, oh no. If you use this seat A, you will get an expectation for using this A, you get to do the conditional expectation, right? You using this A, we get. Let me use another one. If I choose another seat, for example, I choose here. I choose the probability here. I need a 4, 5, right? I choose, or maybe I just choosing. I choose 0.2 here. Okay, a part of this and a part of this. This is my seat. Okay, this is the omega. Okay, this is the omega, right? I choose a little bit. I choose a part of my A taken from where L equals 1 with probability 0.2. I choose another part. So this part, I choose a little bit from here, probability 0.2. I choose a little bit from here. L equals 2.5. Okay. For my new seat A, my new seat A. First of all, for a new seat, the probability of A is still 0.2 plus 0.25, 0.45. What is the expectation of this X, the conditional expectation of this? Oh, it just the first part L takes the value 1 with probability 0.2. The second part takes the value -2 times 0.25 divided by the total probability 4.5, right? Do you agree with me? Do you agree with me? But this, using the second A, you get a smaller value. Because in the expression form, the A you choose satisfies what? It has probability 0.45, no problem. Okay, probability is P of A is always 1 minus alpha. So here is probability 0.45, no problem. But on this C, on this set A, I'll take the largest values, right? L equals 2, the largest value is fully there. L equals 1 is fully there. Probability 1.1 plus 0.3, right? Then the third largest value is L equals -2, right? So you take the largest possible values you can find for L with probability on this set. The total probability is 0.45, but on this set, it takes the largest value. In a second case, yes, you do find a set with probability 0.45. But on this set, L doesn't take the largest values. It takes the value 1 and negative 2. It's not the optimal choice. Does this give you a better understanding of expected form? Expected form is really average of the largest values. Okay. For an arbitrary set A with probability 1 minus alpha, yes, it's the average of a set of probability 1 minus 0.45. But on this set, L doesn't take the largest value. It's not the tail. So I should put an L here. Okay, let's have a break, return at 2:25. Okay, return at 2:25. I really hope this theorem helps you to understand the definition of expected form. Expected form is really the average on a set with probability 1 minus alpha. But when you choose a set, you have to be careful to make sure that you are choosing the largest possible values. So you should check the value of L from the largest to the smallest. Right? So L equal to, for example, for this example, alpha is 0.55, 1 minus alpha is 0.45. The largest value is L equal to. The total probability is 0.01, not enough. So you consider the second largest value, L equals 1. The probability is 0.3. In total, you have probability 4. 0.4, not enough. We need more. You need another small portion of probability 0.05, right? And then you go with the next largest value, L equals -1. That gives you the optimal way, the best A you can have. Right? If you just choose an arbitrary set with probability 0.45 and do the average, it doesn't give you the best, the highest possible value, right? It doesn't give you the largest case. So, right, the optimal A, starting with the largest values of A, the average of the largest values of L, right? That'll give you expected form. Okay. So this theorem actually is a more general with more general case of this theorem. Maybe I should call this corollary. Maybe I should call this corollary. Corollary for discrete random variable. This is for discrete random variables. You can use this to compute the expected form for discrete random variables. Actually, it's true for any random variable. It's fine. So if you compare this one, expected form is the average of the largest values of L with probability 1 minus alpha, right? Now you can get this one, right? It's the average of values of L on a set with probability 1 minus alpha. But especially if I want you to choose the largest value. Okay. Does this theorem make sense to you guys? Any response? I hope so, because this is a very important theorem. This important theorem. I would view the previous statement as the second method for computing, especially for discrete random variables. I would view this as a corollary. This is a main result. Okay, a theorem, which we wouldn't prove. Intuitively, you can understand that. Intuitively, you can understand that, starting from our first example, right? Okay. So now I'm going to give you another corollary for continuous random variables. For a corollary. So let L be such that its CDF its cumulative distribution function f is continuous, doesn't have jumps. Then expression for alpha of L is actually of L L times indicator function of A of probability of A, where A can be chosen to be the seat of omega such that L omega larger than value at a risk of L, right? Because this is a number, this is a real number now, right? So this is a seat, L larger than something. This gives you a seat, it's the seat of omega, right? So for continuous random variables, expression for of L equals, it basically I can tell you, it's the theorem tells you that it's a maximum average on cis L with probability 1 minus alpha. Now, for a continuous case, I tell you which seat will give you the maximum. Which seat will give you the maximum. Right? This seat A is good. Right? So this one. Among all the seats with probability 1 minus alpha, you do the conditional expectation. Now you choose the largest one. If you compare with the discrete random variable, here. For discrete random variable, for this example here, right? The previous example. For this expression for is the maximum of this conditional expectations. But which A will give you the maximum? For discrete random variable, you just start with the largest values until you start with the largest values, L equals 2, L equals 1, L equals minus 1, until you reach the probability 1 minus alpha. Okay, until you reach the probability 1 minus alpha. For continuous random variable, it's easier. You have a better way to find out the A you want. For a discrete one, you start with the largest value 2, 1, minus 1 until you reach the probability 1 minus alpha. For a continuous one, A has a very good expression. A is a seat where L larger than the valid risk. Let's prove this one. I only sketch the ideas of a proof. Sketch a proof. So you see here, I didn't prove. I tell you intuitions. I do hands-on example to lead you to the conclusion, but I didn't give you a rigorous mathematical proof of that because that will take too much time. That takes too much time. I cannot do that. So sketch of a proof. I only need to prove, recall from lecture 2. If f is maybe lecture 2 or 3, I forgot. If f is continuous, then f left arrow alpha equals alpha. Okay, we proved this one when we proved that f left arrow is like the inverse function of f. So if we write this out, what is this? This is the probability of L less than or equal to This definition of CDF equals alpha, right? So another way to say is that the probability of L larger than this guy equals 1 minus alpha, right? And by definition, recall what is the definition of value at risk? It's defined as F left arrow, right? So basically, this one tells me that L larger than value at risk of alpha equals 1 minus alpha. So if I let A equals L, the set L larger than so remember is the percentile, let's say this is the value of risk, right? L larger than the value of risk, right? Okay. So if F is continuous, then this one has probability 1 minus alpha. Okay. This is not a true for discrete random variable. Discrete random variables. It's only true for continuous random variables. So we find a set A with probability 1 minus alpha. Note, on A, L has the largest values. Why L has the largest values? Because A is given by a cutoff. Here is a number, okay? L is above this number. I'm considering all the values. L is above this cutoff. That gives you A. So on a set A, L takes all the values above the value of risk. Let me write it in the next page. So what is A? L largest this one. So basically on A, so maybe I say A is where L takes is where L is takes the values, takes all the value, the values of L larger than a cutoff. So basically, you are considering all the larger values up to what? So you are considering all the larger values of L up to all the larger values of L up to the cut line. Right? Value of risk is just a number, remember. And luckily the seat has probability, and probability of A by our proof above has probability alpha, right? Thus, you can say expression for equals L, the average on A. Remember, L is what? The expression for is what? Average of the largest values on a seat A. On a set A with probability 1 minus alpha, right? Average of largest values on a seat with probability alpha. Now, my A chosen here is the best of A because it contains all the largest values. You start from the largest values, right? Goes down, goes down, goes down until to a point. Now you accumulate a probability alpha, 1 minus alpha. See? Largest includes all the larger values up to a point where you reach probability, accumulated probability 1 minus alpha. So this is the best seat. So another way to see, you are accumulating largest values of L up to a point. You reach probability 1 minus alpha, right? You accumulate largest values of L up to what? Up to the valid risk. Out of the valid risk, exactly we have probability 1 minus alpha. The set A you are considering is L larger than a cutoff point, right? So you are starting from all the largest values are there, right? The larger the better is there, right? You're going from the largest values of L, go down until to a point. Now you have probability 1 minus alpha. And the point, luckily, is just a valid risk. Okay, that's it. So this is good. This is good. Why I use this one? Because we will use this. We need to use this fact. This is just a transition fact. You don't have why I discuss this one? Because I need to prove another theorem. A further theorem which allow you to compute expression for the continuous random variables. So corollary or method two for computing expression for continuous random variables. What is method one? Method one for continuous random variable. Well, it's just definition, expression of alpha, right? Of L. It's just a definition. Right? You find the valid risk, you do the integration, then you get an expression of. Then you get an expression of. But remember, for discrete random variable, we have method one using definition, right? You make a graph of your valid risk, right? Then you do the expectation, right? The method two is just using the factor using average of the largest values of L up to the probability 1 minus alpha. Now for continuous random variable, the method one is still using definition. Method one use definition. But I have another second method for computing expression for continuous random variables is this one. Let L have a probability density function f of t. Then expression for alpha of L equals 1 minus alpha. Let me see, I forget. What is that? Because integration of value at risk from value at risk to infinity, t f of t dt. Okay. Let's see how to do this one. Let's see how to do this one. So for what is nice of this one is that when you do compare with this, you have to do integration of value risk. Here, you're integrating about this one. The density function, it involves density function, right? It involves density function. And it's maybe easier, right? It may be easier, right? So let me show you. Let's prove this one. Let's sketch a proof of this one. And it is for a proof, recall if L has density function PDF f of t, then this one we mentioned in MTH 304 and MTH 700, right? Of L equals what? Equals negative infinity to infinity h of t f of t dt, right? Do you still remember this one? For example, expression of L square or equal to infinity negative infinity t square f of t dt. Expression of e to L equals infinity infinity e to a t power f of t dt, right? Expression of, let's see, what sine L, okay? Just infinity, negative infinity, sine of t, f of t dt, okay? I need this one. Now let's sketch proof of this one by a previous result. We know expression for alpha of L equals what? Equals expectation of L times the indicator function of A. What is A? L larger than value at risk alpha of L. Indicator of A. Probability of this L larger than value at risk alpha. And the bottom, remember the probability of this equals 1 minus alpha for sure. That's why we choose it. So this is expectation of L times, I can rewrite this one as this value at a risk alpha of L to infinity. Then takes L. One minus alpha. These two are the same thing. If L of omega larger than the value risk, it takes the value 1. Otherwise, it takes the value 0. So it's the same thing. Now I consider my function. My function h of t equals t times indicator function of this one. This is basically this is an indicator function on an interval. If a t is inside the interval, it takes the value 1. Otherwise, takes the value 0, right? So the inside thing. So now apply this one with the L you want. With the L you want. This is the inside function, right? It's just h of L, right? The integration from negative infinity to infinity. your h of t is t, then indicate a function of value at risk to infinity of t times f of t dt. What is this? It equals 1 if t is larger than value risk. If t is less than or equal to value risk, it equals 0. So this one means that it equals 1 if t is larger than value risk, otherwise 0. So you can see it is the same as integration from value at risk to infinity t of f of t dt, right? When t is larger than value at risk, it's 1. So the remaining thing is just t times 1 times f of t, just the remaining thing t times f of t. Otherwise, just 0. Right? So if it is 0, we don't integrate it there, right? We only integrate this one when t larger than value risk. Oh, I forgot to divide the bottom. Divide 1 minus alpha. This should be divide 1 minus alpha, the bottom, the denominator. And it's done. If you don't fully understand this proof, at least you should have a feeling about why it is. We just use the result, expectation of h of L equals how to get this into density function. How do we get this into density function? Okay, so this formula is, you need to remember this formula. You will need to use it in your midterm, in your homework, this formula. So you better know how we come to this part, right? Look at them from time to time and ask around if you have questions until you have a reasonable understanding of the proof, how I get there. So now let's look at an example. Let's look at the previous lab. I forgot to download it earlier. Let's look at the normal distribution. Here we are using method 1 to compute it. You really need to know how to do this one. I may put it into midterm, actually, using definition to compute the value risk and the expression of normal distribution, right? If you don't know how to do that, it's not good. So here I'm just using definition, you see, method 1. You just use method 1 to do it, right? And you do some changing of variables, eventually you come to this part. Okay? Well, you have to simplify the integrals, right? You have to simplify the integrals. So here, what I'm doing is that I use s equals phi of t to do the change of variable. If you put it in, what is phi of s? Put s into this one, you just have t left, right? Then d phi of t, right? ds become d phi of t, right? What is d phi of t? The derivative is phi of t times dt, right? So you end up with this one. Think about what I say. You end up with this one. Okay, method 2. This is in a lab, so you should know about it. Now let me do method 2. Method 2 of this example. So L follows a normal distribution mu sigma square. If we compute exponential form of L, by the formula it is this one. Value at a risk infinity times t times the density function. What is the density function of this one? What is the density function? The density function of this one is 2 over 2 pi times sigma e to the minus sigma square x minus mu square. You do not need to memorize the density function. I will give it to you if I need it. T. T doesn't allow me to erase, right? Does it? This is dt. All right. If I use this one, use the second method, it will be this one. I need to do a change of variable. So I do a change of variable t minus mu over sigma equals s. Right. So it becomes 1 minus alpha I think I can simplify it a little bit. Let me do second method a little bit later. Let's do it a little bit later. I have a better way. Oh, we can do this one. The next one. Yeah, we can do this one. This is still method 1, right? Method 1. What is method 2? Is that exponential form of alpha of L equals 1 over 1 minus alpha times value at a risk of L to infinity, t times f of t dt, right? So if I put it in 1 minus alpha, exponential for value risk. Now the function has a value only between a up to b, right? Okay, so you shouldn't use infinity because above b is 0. Above b, this f of t would be 0, so there is nothing to do. So put it to b. And this is t times the density function is 1 over b minus a, then dt, right? Okay, so that's it. So if we do this one, it would be 1 minus alpha times b minus a times integrate of b from alpha value risk to t dt, right? Then you can see the antiderivative of t is what? Is a half t square, right? Half t square evaluated at a b, evaluated at a value at a risk alpha of a. So it would be equal to 1 over 1 minus alpha times 1 over b minus b. This would be, let me take a half out, times a half, then times b squared minus value at risk squared, right? So if we do an expansion, it would be 1 minus alpha times 1 over b minus a times a half. This would be b plus value at risk times b minus value at risk. Difference of square, right? Now let's see what is value at risk. Let's compute this. Remember, value at risk of L is a uniform is A plus alpha times B minus A. So B plus value at risk is just a B plus A plus alpha times B minus A, right? What is it? I don't know, but we will see. What is a B minus value at risk? Is B minus A minus alpha times B minus A. Oh, this is nice because you have B minus A, so it equals 1 minus alpha times B minus A. Right? So this guy exactly equals this one, So it cancels with this one, right? So what it remains just a half of B plus value at risk alpha times L, which equals a half of B plus A plus A plus alpha times B minus A. And then you can verify this equals this. Is it true? Yes, it is equal to that. Okay, you can see they are equal. Okay, it's not that difficult. You just need to do the integrals. Okay, let's review it again. Using method 2, the formula is 1 minus 1 over 1 minus alpha integrated from value at risk to infinity, t times ft. Now your f of x or f of t is 0 if t is above b, right? So you just need to integrate from value at risk up to b, because if t is larger than b, it's 0. There's nothing to integrate. T times density function. What is the density function? 1 over b minus a. So you simplify, take them out. This is it. You get an antiderivative function. You have a difference of squares. You use a difference of square expansion. So 1 over 1 minus alpha times 1 over b minus a times a half times this guy. Now you simplify what is b plus value risk, b minus value risk. You are simplified, get the answer as before. Okay, you can get it as before. So you can see the second method is not necessarily better than the first method. Sometimes the first method is better. Sometimes the second method is better. Okay. Yeah. Sometimes the second method is better. Let me do one more example for you using this one. Example 1, let's do exponential distribution. Exponential distribution. Maybe I later TI do in the lab. Yes, I later TI do in the lab. Okay, now let me summarize properties of expression order form. Properties of expression order form of ES as a risk measure. First of all, like a value at risk, expression order form of L. Sorry. If L1 is less than L2, so L2 is larger loss operation, then expression order form of L is less than or equal to expression order form. So Basically, it says that a larger loss operation gave you a larger risk. Proof is easy. Recall, if L1 is less than or equal to L2, then we have proved it for a valid risk. Now, what expected for is the integration rate. EU. So this is less than or equal to 1 over 1 minus alpha integration from alpha. This is the valid risk of L1 is less than or equal to valid risk of L2. So you get that. And this is just a valid risk of L2. So good. Second thing is that if C is a constant, then like a valid risk, is beta for is translation invariant. L plus C, you can, if you add a constant doesn't, you can take it out. You can take it out. The proof is still the same because this is true for valid risk and expected value is average of valid risk, right? So expected for of L plus C, what is that? It is 1 over, it's a value at a risk integrate, value at a risk of L plus C, right? du. And value for valid risk, you have it equals valid risk of L plus a constant C, then du, right? So you can split it as 1 plus alpha plus 1 minus alpha 1 constant C du. And the integral of this is just average of C, just C, right? So this one, oh, what is this? By definition, this is just expression for of L. And the second one, if you compute the integrator of a constant, right? So it's just, so no problem, no problem, no problem. The third property is this one. If lambda is larger than or equal to 0, then expression for alpha of lambda L equals lambda expression for of L. Again, this is true because it is true for a valid risk equals 1 over 1 minus alpha 1. For valid risk, you can take the lambda out, right? So you can take the lambda out. I can put this out, so it equals lambda times. And this equals lambda times expression for alpha of. If lambda is larger than or equal to 0, then expression of. Okay, this all follows from that valid risk, which we have proved before. Now, what is good is that if especially for it actually respects subadditivity for any L1, L2, especially for alpha of L1 plus L2. Remember, it fails for valid risk, but it is true for especially for. And let's prove it by theorem. Oh. I can do this one. Let A be any seed with probability 1 minus alpha. Then we have expectation of L1 plus L2, right? You consider the conditional expectation of this guy on A is defined this way, right? And it is equal to conditional expectation over A plus conditional expectation of L2 on A, right? And this guy, because A has probability 1 minus alpha, this guy is less than or equal to by theorem. This guy is less than expected for of L1. And this guy is less than or equal to expected for of L2. Right? Let's recall what theorem I'm referring to. This one. This one. The expected for of L is maximum conditional expectation of L over any seat with probability 1 minus alpha, right? So for an arbitrary A, the conditional expression is always less than or equal to expected form. That is what I'm using. So L is any seat with probability 1 minus alpha, right? Right? So what I have is that, so for any seat A with probability equals 1 minus alpha, we have L, the conditional expression of L1 plus L2 on A is always less than or equal to this one. Right? It's always true. But remember, because this is true for any A, right? This is true for any A. This guy is always bounded by this one, right? But if we choose an optimal A for L1 plus L2, what do we have? Taking maximum, taking the best A for L1 plus L2 in the left. What do you have? The left will just be equal to expression for of L1 plus L2, right? This is the left. The left is true for any A with probability 1 minus alpha. Why don't we choose the best A for L1 plus L2? L1 plus L2 is a random variable, right? Okay, so that is a conditional expectation on A for us for L1 plus L2. Now I choose the best A for the sum, and it becomes expected for. But for whatever A, it is still less than or equal to this one, right? So yeah, this lecture is a little bit theoretical. It's a little bit theoretical. A lot of arguments, but they are approachable. You just need to be patient and sit down, patient, spend a few nights to go over them. If you are impatient, then you cannot study mathematics. Mathematics need a deep and careful thinking. You have to sit there, be quiet, forget about the word, the rest of the word. Think about them, then you will be fine. So I have proved for expected for yes, luckily, we do have that. We do have that. It is the subadditivity holds. Okay. So now we can introduce some properties. Later, a mapping. I'm mapping on random variables. I'm mapping row of L is a real number. Is called a monitoring. It's called a coherent risk measure. Coherent risk measure. If row if for L1 less than equal to L2, row of L1 less than or equal to a row of L2. Second, for any lambda larger than equal to 0, row of L, lambda L equals lambda of row L. Third, oh, no, switch. Row of L plus C equals row of L plus C. C is a constant in R. For any lambda larger than equal to 0, row of lambda L equals lambda row L. For row of L1 plus L2 less than or equal to row of L1 plus row of L2. Right? So if it satisfies these four properties, people love it. It's called a coherent risk measure. The sum up by the previous arguments, we know exponential form is a coherent risk measure. It satisfies these four properties, coherent risk measure. Value at risk is not, because it fails the subadditivity. That doesn't satisfy the fourth condition. So we are getting better. We are getting better, right? We have finished everything about exponential for pretty much. But I have a example which I promised you, right? About the computing example. Computing exponential for of L, where L is a normal distribution. Now I do it using method 2, using method 2. Solution. Note, L is a normal distribution, so L can be written as mu plus sigma z, where z is a standard normal distribution. We talked about this in MTH 700, right? Mu, sigma, standard deviation, basic standardization, right? Basically standardization. How do you prove this one? We have proved that you just define this one as L minus mu over sigma, right? We know standardization gave you standard normal distribution, right? Now, if you solve this out, you will have that L equals mu plus sigma z, right? So how do you find a z? Z is just a standardization. Now we have exponential for alpha of L equals exponential for alpha of what? Of mu plus sigma z. I'm using property 2, it will give me that, just a computer exponential for of sigma z plus mu. We can take a constant out by 2 above. By 2 above. Now sigma can be taken out. What is it? It is sigma times exponential for alpha of z plus mu. Here I'm using by 3 above. Right? If it's a multiple, scalar multiple, it's a number, sigma, right? You can point out. So now all I need to do, this is mu. All I need to do is just computing exponential for standard normal distribution. So I do it the next page. Exponential for standard normal distribution. What is it equal to? Well, by the formula, the second method formula is it equals this one. Infinity, t times the density function. The density function of standard normal is this one. So if you do it out, put it out, it becomes this one. Infinity. This is t times e negative t squared dt. This one has an antiderivative. If you don't know the antiderivative, you can do the change of variable using half t squared equals s. This would be, and this would be this. If you do, you can either directly find the change of the antiderivative, or you can do the change of variable. It is actually equal to minus of this. Let me say whether it is correct. Yes. Yes. So if you do it, it will minus times. This would be minus a half of value at a risk of z squared. And what is, recall, what is value at risk of z? It's mu plus 6, it's mu is 0, is mean plus its standard deviation times the phi inverse of alpha, right? So equal phi inverse of alpha. Right? You can directly get it because value risk is just is a reverse function of CDF. So you can write it as 1 minus alpha times 1 alpha square of 2 phi of negative phi inverse of alpha square. If you think about this, what is the density function? So this one can be written as 1 minus alpha. What remains is really just the phi of inverse of alpha, right? I think it's simpler, right? It's simpler than the lab. That is method 1. This is method 2. You have to know how to do this computer, especially for continuous random variables, for both methods, method 1 and method 2, and also know how to do computer value, especially for discrete random variables. Still 2 methods, method 1 and method 2. Okay. You have to know all of these in total. Discrete 2 methods, continuous 2 methods. Okay. Now you can put in this expression for value for standard normal. Put it here, you get what you want. You get what you want. So expression for, I have finished everything about them. 2 computation methods, right? Method 1, method 2. Method 1, method 2. Okay, for discrete and continuous. Then I use this and that way we proved the properties of expression for. Expression for satisfies 4 properties. 4 properties. There's 4 properties. So it is a coherent risk method. Value at risk is not. So what time is it? Let's return after 6 minutes. Then I will talk about the computation of them. No, using data, how to estimate them using. I'm not sure whether I did a recording for a second part. I cannot really focus today. So let's talk about how to estimate these things in using data. So you simulate given a distribution, given a a CDF, right? Or whatever, or the distribution, for example, or distribution. Usually a distribution is characterized by a CDF, right? Let's see, for example, normal distribution, right? How do you estimate this? You have data, similar data, x1 to xn, right? Xn can be large, right? Xn can be large. Okay, simulate. Then it's actually not that difficult to estimate value risk. We will see. So what do we do is that first of all, order them from smallest to largest. Okay, let's call it x tilde 1, x2 tilde. The same numbers, just reorder them. When you simulate them, there is no order. I want to make sure that you are starting from the smallest to the largest, right? Then we define how do we define value risk tilde alpha. I define it as alpha. I put a capital N there to show that it's that of L. CDF. The same as L. L CDF. Okay. Then we define this one as what? As alpha, and this is the alpha times n, take the integer apart. Alpha times n takes the integer apart. Basically, like alpha is 0.99. If alpha is 0.99, then alpha n is pretty much the 99th percentile, right? You order your data. You order your data. You order your data like this, then take a cut off at the 99 percentile region, right? Okay. Then we can also define the space shortfall. I will put the capital N to show that we have n data used, right? So what is it? We define it as, you have to define it as an average of a tail, right? So what are the tails? Xk tilde, where k is larger than or equal to alpha n, right? Starting from your value risk position to the last one. You do the average. So how many items do you have? You can put k plus 1. It's okay. Right? So the tail, all the terms in a tail. Then you have to do an average, right? How many of them do you use? M minus alpha n. Okay, there's many terms. There's many terms. Now the theorem says that first of all, the estimation of expected shortfall, no problem. It always converges to expected shortfall of L for any alpha in between 0 and 1. But for value at risk, it may have a problem. Value at risk alpha and tilde. It converges only under a condition. If value at risk U is continuous at alpha. If it is not a continuous there, you have problems. So Because the convergence basically means that if n is large, right? This means that, what does this mean? It means that if n is large, then this guy is close to the expression for you are using, right? So now we can simulate data, then using data to estimate your expression for, right? If n is larger, the estimation would be more accurate. Now as a function of u, now for value risk, if a value risk, which is just a rate, you can write it as of L. Basically, it says that if f left arrow, if f left arrow is continuous at alpha, or value risk is continuous at alpha, as a function of alpha, right? As a function of u, if it is continuous at alpha, then the value risk converges. Otherwise, it's not. I will give you an example to explain why. Under this condition, you will have that the value risk defined here, right? This is pretty much approximately equal to the real value of value risk. So you can use them to do the estimation. You can use them to do the estimation. So using data, how do you estimate? As simple as this. As simple as this. Let me give you an example of why value at risk may not converge. Consider this one. Consider probability of L equals 1. Take the value 0.5. There's a distribution counting the number of hits of a fair coin. If you flip a fair coin, L is the number of hits in each flip. It's either equal 1, you get a 1 hit in a flip, or you get a 0 hits, you get a tail. Okay? So for this one, what is the value risk of this one? U of L. Like if you check a graph, it looks like this. Either it equals 0, left continuous to 0.5, this point. And for remaining, it is this one. It is this one. Okay, and this value is 1. You can see value is not continuous at u equals 0.5, right? So you cannot use data to estimate value at risk 0.5 of L, because at a 0.5 there is a jump. Why is that? Why is that? Let's say n equals 1,000. You simulate 1,000 data. Flip a coin. Basically, flip a coin. Flip a coin 1,000 times. So it may happen because it's a fair coin, right? So you may have 0, 0. Let's reorder them, right? You may have, let's say you have how many hits do you have? Well, it's a fair coin, so it's probably approximate 500, right? Let's say 501. It may also have, so it has 499 hits, right? Okay, if you reorder them, of course you may have hit, tail, 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 hit, tail, tail, tail. It's disordered, right? So I reorder them. Okay, so you have 499 zeros, 501 hits, 499 tails, right? So if you do this one, I ask you, what is this one? What is this? What is 0.5 1,000 estimate of L, right? It's defined as x 0.5 alpha n, right? The 500 one, right? So this is just a x 500 tilde, right? So from a smallest to a largest, choose a 500 one. The 500 one would be 1, right? Would be 1. It may also happen that you flip it again for 1,000 times. It may happen that you have actually 502 tails, right? 498 heads, right? It may happen this way. It's definitely could happen, right? Then what is valid risk of this one? Estimates of this one. What is it? Oh, it's just x 500 tilde, right? So from smallest counter to the 501 is 0. You can see because when you flip it, there is always either you have 500 of flip, it's the number of heads of or tails is around 500, but you can flip around it, right? Today you flip it for 1,000 times. Tomorrow you flip it for another 1,000 times. The day after tomorrow you flip it for another 1,000 times, right? But your estimated valid risk is not stable. Today it may be 1, tomorrow may be 0, right? It's jumping between two numbers, 0 and 1, not stable. It could be 0, today it could be 0, tomorrow it may be 1. It's not converging anywhere. Even if you make n larger, even if you make not 1,000 times, if you make it to be 10 million times, a billion times, n is a trillion, right? Still cutting in the middle, right? You may have one more head or one less head. Even this will change your estimate. It's either 0 or 1. It's not stable. But why does x-bishutful has no problem? Because it's average, right? For x-bishutful, what is x-bishutful? X-bishutful, 0.5. Right? It's the average of a last 500, maybe 501. Okay? The largest numbers do average. If you have one more 0, one less 0, does not matter. Right? Does not matter. Okay? It doesn't change the value of estimate a lot. But for valid risk, it's really jumping between two numbers. Okay, so it could have huge problem. Another way of estimating this is that, another way. That way, the previous way is brutal, right? Yes, too coarse, too brutal. Another way is that, let's say you have a population, you have a distribution. You don't know the distribution. You have data. So first of all, test the data is normal. You can test whether the data is normal or not. If you test the data is normal, then life is easier. Then life is easier. Why is that? Because normal distribution, value risk of a normal distribution. If L follows a normal distribution, right? We have formulas for them, right? Because, for example, this is mu plus sigma times phi inverse of alpha. This one, you can check a table. This one, you estimate using data. Estimate using data, right? This also has a formula. mu plus sigma times something I forgot. Times something. Maybe 1 over alpha, 1 over 1 minus alpha times. I forgot it. It's probably something like this. Likely. I forgot about it. Check. So if you know, if you can test that the data is from a normal distribution, is from a normal distribution, then you are fine. Then you are fine. Then you are fine. If you cannot test whether it is from a normal distribution, in the lab, I will provide 2 tests to do that. 2 tests to do that. Okay, to test whether the data is from a normal distribution. One is for a small sample size, one is for a large sample size. If you test that the data is from a normal distribution, then you can apply this method. If you cannot test whether data is from normal distribution or not, then you have to apply the previous brutal method here. Here. Okay. So let's finish here. Again, the midterm coverage covers up to today's lecture. I will upload the homework 1 and project 1.